The GE115B remains one of aviation's most powerful turbofans, capable of immense force during peak testing.
While its maximum potential is legendary, commercial variants are regulated to a steady 115,000 pounds.
Managing this power requires a sophisticated electronic brain to ensure safety and longevity across various environments. The Electronic Engine Control, or EEC, monitors the throttle position to adjust fuel flow and shaft speed.
To maintain rated thrust, the engine must manage a consistent mass flow rate through the entire assembly. This rate is determined by the air's density, its velocity, and the physical area of the intake.
The EEC prioritizes N1 shaft speed control because it influences both the bypass and the core airflow. Ambient air temperature is a critical variable, tracked by sensors on the cowl and the fuselage. To stabilize performance, the engine uses a rating plug to calibrate the software for specific thrust limits.
Transitioning to reverse thrust requires the primary forward levers to be moved into the idle detent position. An integrated interlock system prevents the reverse levers from moving until the forward thrust is fully neutralized.
Once engaged, the reverse idle position triggers the hydraulic systems to begin the physical transformation of the cowling.
The EEC commands the isolation valve to open, allowing high-pressure fluid to enter the thrust reverser circuit. A directional control valve then routes this hydraulic force to 6 actuators located around the engine's circumference. These actuators push the outer sleeve rearward, mechanically deploying internal blocker doors across the bypass air path. Blocked air is redirected through cascade vanes, creating a counterforce that assists the aircraft in slowing down. Sensors relay the exact position to the cockpit, where an indicator light changes from amber to green. Pilots can then increase reverse power, prompting the EEC to boost fuel flow for maximum braking efficiency.
Interestingly, the central core still exhausts rearward, while the massive volume of bypass air provides the stopping power.
To stow the reverser, the reverse thrust lever is returned to the idle position, slowing the engine.
Once the engine reaches a stable idle speed, the levers are moved to the fully stowed position. The directional control valve reverses hydraulic flow, pulling the actuators and the outer sleeve back to forward. As the sleeve closes, the blocker doors open, restoring the bypass air's original path for forward thrust.
The EEC then closes the isolation valve, deactivating the hydraulic circuit and locking the reverser system.
For the final shutdown, the fuel control switch is moved to the cutoff position to stop combustion.
Closing the fuel valve halts the chemical energy, causing the engine's rotating components to begin decelerating.
At 7% shaft speed, the dedicated alternator cuts out, and the EEC switches to aircraft battery. After 5 minutes of inactivity, the system completely powers down, concluding the operation of the GE90 turbofan.
Beyond pure power, the engine incorporates a multi-layered fire protection system to safeguard the aircraft during emergencies. Dual-loop overheat detectors monitor critical zones, ensuring that any thermal anomaly is reported instantly to the flight deck.
To protect internal accessories, the core compartment cooling system uses bypass air to maintain optimal hardware temperatures.
Structural resilience is proven through rigorous testing, including high-speed ingestion of large objects to verify blade containment.
The GE90 is also designed to withstand extreme weather, processing massive amounts of water and ice without flameout.
Modern maintenance relies on 24-hour remote monitoring, tracking thousands of data points from every single flight. Each engine has a unique digital twin, a virtual replica used to predict maintenance needs before parts fail.
This engineering excellence created the distinctive buzzing sound that has become the acoustic signature of the 777.
The legacy continues with the GE9X, which utilizes larger, more advanced composite blades for even greater efficiency.
From the GE90 to the future, these giants continue to redefine the boundaries of wide-body aviation power.
Maintaining these titans involves precision inspections, where fiber optic cameras explore every inch of the high-pressure turbine.
Optimization continues through advanced software, minimizing carbon emissions while maximizing the thrust-to-weight ratio of the aircraft.
Engineers also prioritize sound reduction, using specialized acoustic linings to dampen the roar of the massive intake.
The GE90's legendary reliability earned it record-breaking ETOPS ratings, allowing it to fly hours away from land. After thousands of cycles, the engine undergoes a total teardown, returning to a near zero-time condition for continued service. With millions of flight hours logged, the fleet remains a cornerstone of global trade and international travel.
Highly skilled technicians use augmented reality tools to visualize complex assemblies, ensuring perfect precision during every repair.
Beyond its utility, the engine's aesthetic beauty is celebrated, with its fan blades displayed in modern art museums.
The future sees these engines transitioning to sustainable fuels, aiming for a net zero impact on the global environment.
As aviation evolves, the GE90 remains a testament to human ingenuity and the pursuit of technological perfection.
The low-pressure turbine features 6 stages of blades, extracting energy to drive the massive front fan assembly. Within the high-pressure turbine, single crystal superalloys withstand extreme heat that would melt conventional steel components.
Active clearance control systems use cooled air to manage the gap between turbine blades and the engine casing. To prevent compressor stalls, variable stator vanes adjust their angle to optimize airflow during rapid throttle changes.
The 115B's signature swept blades are crafted from over 800 layers of 3D woven carbon fiber.
Power for the aircraft is extracted via the accessory gearbox, driving the generators and hydraulic pumps.
A dedicated oil system lubricates 5 main bearings, while scavenge pumps return fluid through a master filter. Fuel oil heat exchangers serve a dual purpose, cooling the engine oil while simultaneously pre-warming the fuel.
The modular architecture allows technicians to replace entire sections, such as the fan module, without a full overhaul.
This final blueprint view reveals the intricate harmony of thousands of parts working as a single machine.